Hi guys, welcome back to ASFC Physics. In today's video, we're actually going to be discussing a special topic, no pun intended, which is not on the spec, and namely Einstein's theory of special relativity and time dilation. Now, where did this theory actually arrive from? The answer is Maxwell's equations of the electromagnetic field. We can see that these equations over here written just here, they were actually the pinnacle of theoretical physics in the 19th century. We don't need to understand them just yet, but I just wanted to illustrate this. Einstein studied these really intensively. In fact, he truly believed that they were a beautiful set of mathematical and physics thinking, and if you look really closely into them, number one, they show that all electromagnetic waves travel at the speed of light, 3 times 10 to the 8. But number two, they have a strange consequence that the speed of light is constant in all frames of reference. Well, Einstein used this together with some very important thought experiments to come up with two postulates of special relativity. Number one, the laws of physics are the same in all inertial frames of reference. The word inertial here means just constant speed, so we're not dealing yet with acceleration. Number two is that the speed of light, c, is the same in all frames of reference. So light is always propagated in empty space with a definite velocity c that is independent of the state of motion of the emitting object. This is really bizarre. Let me show you why. Imagine you have a car over here, and from that car, let's say the car is moving to the right at 20 meters per second. Suddenly you emit or you throw an apple at 10 meters per second. This is our sort of apple just here, or any other object. Now, in your frame of reference, the speed of the apple is 10 meters per second. So you can just say that, let's call it v, the v of the apple is 10 meters per second. However, if you ask somebody who is just standing on the road what the speed of the apple is, well, in their frame of reference, that speed is actually 30 meters per second, because the car was already going at 20, and on top of that, you added victorially the speed of the apple. Light does not work that way, according to Einstein. It's very, very bizarre. If you switch on your headlights, and in your frame of reference, the speed of light is c, just 3.0 times 10 to the 8 meters per second, to somebody sitting on the road, the speed of light will be exactly the same. It's going to be c is equal to 3.0 times 10 to the 8 meters per second. This has some really bizarre consequences, and we're going to be looking at those. The only way to actually keep the speed of light constant, because speed in general, at least for average speed or constant speed, speed is just distance over time. So the only way to keep the speed of light constant is to change either the distance or the time. And in fact, they do change. And that's what we're going to discuss. We're going to start off with the first one, which is how time changes in time dilation. Okay, well, let's move down along here, and we're going to look at some diagrams in particular. First off, the first diagram shows us a pretty simple experiment. We've got two mirrors. We've got mirror A and mirror B. We send a light pulse upwards, which is just reflected and bounces back downwards to the second mirror. Now, in this case, delta t, the time for this event to happen for a light beam, for this red light beam to go upwards and then downwards, is just the distance over the speed. Well, our distance is going to be 2L. Why is it 2L? Because it goes there, then it comes back. So it travels the distance of L twice, divided by the speed, c. Remember, the speed of light is always the same. In the following case, on the right, we've got the speed, we've got exactly the same operators, however, it's moving to the right. Now, the trajectory that you're going to see as an observer who is completely stationary and there's somebody's moving both mirrors and the flashlight or the laser, whatever it is, to the right, is that of a diagonal. That just comes from vector addition. You can convince yourself with that. You can ask somebody to sort of slowly moving a pen upwards and downwards, and then just ask them to move to the right. You're going to see that trajectory when they do that. Well, let's say that in this case, that light travels a different diagonal distance d. So in this case, delta t primed is just going to be 2d over c. Now, something here which it might be worth just pausing the video and convincing yourself that that's the case. But if the speed of this whole apparatus moving to the right is v, then because distance is speed times time, say v times t, and let's say this whole time that let's say that this this distance here is going to be v times delta t primed. Remember, t primed is the time when in the frame of reference of the object that is moving to the right. Okay, well, half of this distance will actually be a half times v times delta t primed. And now I have all of the three sides of a Pythagoras triangle, which will probably come in handy later. Okay, well, just to recap, on the left we've got an equation for delta t, stationary frame of reference. On the right we've got an equation for delta t primed, frame of reference which is moving to the right at speed v. Okay, well, can we find a link between those two equations? My first stop will be to try and use Pythagoras. So let's just apply Pythagoras for this triangle over here. We're going to see that d squared hypotenuse is going to equal L squared plus the other side. So let's just write that down. So I'm going to write it as d squared is equal to L squared plus a half v delta t primed, all of it squared. Okay, well, once I have this, all I need to do is, well, I'm going to need to plug in an expression for d, but I've got an equation for d over here, so I'm just going to rearrange this one for d. So let's say that d is going to equal c delta t primed divided by 2. Okay, perfect. Now that I've got this, all I need to do is plug that in there. So if that's the case, I'm going to get that c delta t primed over 2, all of it squared, is equal to L squared. Well, let's go back into the other equation and see if we can figure out an equation for L in exactly the same way. Well, we can, so we can just say that L, we just need to bring the c up here, is going to be c delta t divided by 2. Okay, well, let's just write that. It's L squared. Let's not forget the squared. So we're going to get c delta t over 2. All of it is squared plus a half v delta t primed squared. Perfect. Okay, well, now we can first of all get rid of this factor of 2 because that's present in all of our equations, and now we can We can just expand some brackets, so we can just say that c delta t primed squared is equal to c delta t squared plus v delta t primed squared, and there's squares here as well. We need to group the equations for delta t primed on one side, so I'm going to bring this last term on the left, and I'm going to get c squared delta t primed squared minus v squared delta t primed squared being equal to c squared delta t squared. Now, a trick in this derivation in special relativity would be to divide both sides by c squared. And if we do that, in fact, let me just show you how to do this. I'm just going to divide everything by c squared. That's going to get cancelled, that's going to get cancelled. So what I'm left with is delta t prime squared minus v squared delta t prime squared over c squared, and that's going to equal delta t squared onto the other side. Okay, I'm almost there. I almost have an equation for delta t prime squared with respect to delta t. So all I need to do is just factorize and put to one side. So I get that delta t primed squared is equal to 1 minus v squared over c squared, which is equal to delta t prime squared. Now I'm going to square root both sides as well. And actually let's first just rearrange for delta t prime squared before we square root. So delta t prime squared is going to equal delta t squared divided by 1 minus v squared over c squared. And now I'm going to take the square root of both sides. I'm going to get that delta t prime is equal to delta t squared over the square root of 1 minus v squared over c squared. Now, this is one of the most important results in special relativity, really, which is time dilation, the equation for time dilation. This tells us that if we're moving at an inertial frame with a speed v, our measured time will actually change. If our speed is not close to the speed of light, for example, I did some calculations and you can check those, but if v is equal to 100 meters per second, then delta t primed is equal to delta t times 1, or let's just say divided by 1 minus 100 squared over c squared, where c is the speed of light, of course. And if you plug those numbers into a calculator, we're going to get 1.00, those 14 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then there's a 5, 6 over here. So that's as a factor of delta t. So we can just write that over here times delta t. So it's negligible. It's essentially 1. In fact, in your calculator, it probably appeared as 1 because there's not enough placeholders for this number to be displayed. However, if we're moving really close to the speed of light, we can just say that delta t, let's calculate delta t primed when we're moving at 2.0 times or 2 times 10 to the 8, so quite close to the speed of light. So if that's the case, this will be equal to 1 minus 2 times 10 to the 8 over 3.0 times 10 to the 8. All of this is squared. If we plug that into a calculator, we should get that this is equal to about 1.34 delta t. So now for every second elapsed in delta t, our inertial frame of reference, our moving observer, the clock is going to tick slower. 1 second here is going to be 1.34 seconds there. So time is not constant. Time can sort of stretch. Well, it can speed up and slow down. And if you enjoy physics, you've probably seen some programs in which they've noticed that everything that has mass cannot really reach the speed of light. We can see how this is inbuilt in this equation. Let's set that if we're traveling at the speed of light c, then delta t primed will then be equal to delta t over the square root of 1 minus c squared over c squared. Well, that's equal to 1, so that's going to be equal to delta t over 1 minus 1 is 0, so that's going to be the square root of 0. Well, that's undefined. For the mathematicians out there, you will know that the limit of this function is, as this approaches 0, this function, delta t primed, the time, will actually start approaching infinity. So time will be slowing down by such a large margin, it will be approaching infinity. Of course, you can never really quite get there in physics, but yeah, it will be slowing down immensely. This is remarkable. It is an absolutely crazy idea that was also tested by experimental methods and been tested numerous times. In 1971, they took 2 planes and they took them flying around the world for about twice around the world, and they had cesium atomic clocks, and then compared them with 2 other cesium atomic clocks that were left on the Earth, and the results when the 2 clocks were compared was exactly the same as Einstein would have predicted, as the theory of special relativity would have predicted. In fact, they differed by 40 billionths of a second, 40 nanoseconds. Okay guys, this was quite a long video. Hopefully you've enjoyed that. Hopefully you've found a little bit more information on the theory of special relativity. If you didn't understand any of the individual steps, feel free to drop a comment down below. Additionally, if you took some time to understand this, well done. You've done fantastically well to cover this this really interesting and challenging topic. Well done.